Welcome to the March 2022 Engineering Series guest speaker of NORR Ed. My name is Kevin Cooper. I'm a director of NORR in Glasgow, here in Scotland, and I'm the UK NORR Ed leader. Our guest speaker today will be joining us from the City of London. NORR Ed is a continuing education programme founded by NORR 15 years ago, and it's got three main goals, and these are to teach, to learn, and to improve, and to do that continuously. The programme relies on bringing the best guest speakers in the series, architecture and engineering, both of which are of equal importance, building design, and the master series as well, so that we can learn from the great architects and engineers of the past. Each of the NORR Ed sessions starting in 2020 have been recorded with the guest speaker's permission, and these are available on NORR Ed on our YouTube channel for global access. And today's session will be posted 1 week from now, and I would really recommend that you have a look at that. Some great stuff in there. Word of welcome to all of the staff in our 14 NORR offices around the world, and to some of our invited guests globally as well. We've got a real good mixture of guests today. And welcome also finally to our invited students from the 10 schools of architecture in Canada, the USA and the UK. We're glad to be able to contribute this programme to the educational community. So now I would like to ask our NORR Chair, founder and host of NORR Ed, Silvio Baldassarre, to introduce our guest speaker. Thank you.
In 2021, Arup celebrated 75 years. As I noted in my email introduction, Uwe Arup is one of the very few engineers remembered for a building over the architect, and that was the Sydney Opera House. In March of 1966, the Royal Institute of British Architects, RIBA, awarded the gold medal not to an architect, but to an engineer, Uwe Arup. So why is this so significant? Because we generally, as architects and the public, rarely give credit or even know who the engineer is for most of the great buildings of the world. Walter Gropius, the founder of the Bauhaus over 100 years ago, in a letter to Uwe Arup in 1966 wrote, and I quote, "The next generation of architects and engineers would do well to aim towards understanding and accepting the collaborative process, as this was the only means of ensuring the most robust competition of the collaboration process. Within this process, the final control will fall to the individual who had the broadest scope and is willing to accept from his teammates everything that can enrich the total conception. You have shown evidence in your work that this can be done by an architect or an engineer." End of quote. Maybe today, March of 2022, we can remember what Walter Gropius professed about design in his letter to Uwe Arup in 1966, that architecture begins after engineering ends. Welcome to this NORR Ed engineering series today, as we feature our guest speaker, an internationally recognized structural engineer, and an engineer that I hope you will remember after the presentation today. I'm proud to welcome William Algaard, Director, Structures, Arup, London office. William has a PhD in civil engineering from the University of Glasgow. William also has a Master in Civil Engineering from the University of Glasgow and a Master of Sustainability Leadership from Cambridge University. He is Arup's London Tall Building Skills Leader and has worked on tall buildings in North and South America, Europe, UK, and Asia. William has a background from academic research and Arup's Advanced Digital Engineering Group. He has developed a broad range of specialist skills in advanced analytical approaches within dynamics, blast, seismic engineering, and nonlinear response. In 2005, William joined Arup's building group in London, where he led the engineering design and delivery of signature project elements at the Art Institute of Chicago. The last decade, William has acted as a structural engineer, leader, and project director for a broad range of projects, such as the International Whittle School developments, the A25 complex in Taipei, and the CERN Science Gateway. William continues in the Arab culture and tradition set over 75 years ago, challenging convention, collaborating with architects, applying first principle technical approaches and advanced analytical methods to realize elegant engineering architectural solutions. I will now ask William to share his presentation, Challenging Convention and Inquisitive Structural Design Ideology. I turn it over to William.
Thanks, Silvio, for that great and generous introduction. And thanks also for the opportunity to come here and speak today and contribute to your great program. It's a rare privilege to get such a slot, and particularly get a whole hour to speak about essentially a topic of your choice. So that was quite an exciting thing to do, and also quite an interesting task to prepare for this and to review some of the work I've been doing for more than 20 years and then get the chance to share that with you. So I'm very much looking forward to showing you some of this, and also particularly to the discussion afterwards, which I hope and think will be interesting and exciting. So, challenging convention and inquisitive structural design ideology. What do I really mean by that? Primarily, it relates to first principles approaches. And with that, what I mean is not just going by what's been done before, what's the code approach, what is the safe and easy option, and not prejudging what these solutions or outcomes should be, and being willing to push some boundaries. So I'll aim to show how the approach I adopt today in my role as a structural design engineer, primarily on buildings, how that's been shaped by the experience I've gained along the way. Same, I think, applies probably to all of us, that we are shaped by our journeys, both professionally and otherwise. But because the experience is so individual, I've made the focus of the talk today quite personal, and it's, of course, it's also much easier to speak about my personal history and what I've learned along the way. But I'm hoping to share some of that, and also during my career, I do aim to always share the results of the work I complete as much as possible, because it's a quick way for others to pick it up. So the top 5 images here are sort of slightly bizarre. These are from the initial period of my research. So these, starting at the top left, this is from academic research. And then the next 4 are from my early career within the specialist advanced analysis and R&D team at Arup in London. So these things include a pseudo-physical testing approach, ship analysis, impact analysis due to dropped objects, masonry arch integrity analysis, and the development of a floor damping system. So I'll cover all of these topics pretty quickly. Then I'll move into maybe what's more applicable to most people on the call, which is related to building design. So I'll start off talking about the footbridge at the Art Institute in Chicago. And I know there's probably some people on the call from Chicago, so they will recognize this. I'll then talk about the Dubai Sports Complex, which is the middle image, and then a number of tall building projects, BBVA in Mexico City, Yongsan Landmark Tower in Seoul. This is a project that wasn't built, but there are so many interesting aspects that I've chosen to include it nonetheless. And the A25 or Fubon Tower in Taipei, which is the kind of left of middle at the bottom. Atrio and Bogota, Atrio in Bogota, and then Punta Chapultepec or Reforma 5 and 9 in Mexico City are the two bottom right projects. These both use what's called a multi-story special concentric brace system, and they were developed at the same time. So I will be talking a bit about those two. But of course, in between all of these towers, I'll also talk about Centro Botín in Santander, which is the bottom left project, an absolute gem of a project, so unique in so many ways. Common threads in what I'll talk about is dynamics and vibration and the impact these might have on design, but also other impacts where structural engineering drivers have a large impact on the design and architecture. So I know it's a mixed audience with architects, engineers, and students. So I'll aim to strike a balance between technical aspects and how these interact with the design and are connected to each other. An underlying thread through most of these relates to structural efficiency and low carbon design, which I consider essentially fundamental aspect of good design. And I'm, as I said, certainly hoping for a good discussion afterwards. So start preparing those questions and hopefully we can pick up on whatever you find the most interesting later on. After graduating, I decided to stay at university and completed research within something called pseudodynamic testing. This is an approach relevant to seismic design of buildings where we model part of the system numerically or on the computer and other parts physically. The physical model is meant to capture the complex and tricky non-linear behavior, such as cracked concrete, and then other variables are represented computationally without any difficulty or compromise. This was done at Glasgow University, and I know there are people from Glasgow on the call, so it's great to be able to talk about this work that I did in the very late 90s. So even though I consider this work quite interesting, and the concept really does work, the splitting the model between the lab and the computer, and I'd argue I made many important developments, or at least I thought they were important at the time. But my advice would be to any students on the call to think about doing the research in collaboration with industry and avoid this being sort of in an academic bubble, because I'm not totally convinced mine was as well linked to reality as it could have been. And it's important to try to make the work as applicable as possible. But certainly for me, my own personal experience was that the mindset of an experimental approach that I developed during this period is something that still influences me as an engineering designer today. So you might be asking, what does this have to do with architects or building engineers? And the answer will be not very much. It's one of the things I worked on not long after having joined Arup in 2001, 2002. And I completed some detailed stress and buckling analysis on this floating production, storage and offloading vessel in the North Sea. So the link here really is around the tools and the analytical approach that I picked up during that work, which I've since applied to design projects later on. Another unusual project, here I was looking at the behavior of floor slabs due to steel sections being dropped onto them during construction. The initial motivation for the project was around site safety, and whether floor slabs could provide sufficient impact resistance to allow workers to work on floors immediately underneath locations where steel sections were being erected. The takeaway for me on this project was building a deeper understanding of the behavior of materials under extreme conditions and under large deflections. And also the concept that you can calculate most things. And if you do it correctly, you can actually develop a really good representation of even the most complex structural behavior like this. And so it's definitely helped shape the approach and the trust I have in analytical techniques I apply today. And also when I prepared for this talk, one of my surprising findings was that the publication we made on this work, which was only a couple of months, was actually cited in many more publications than my work at university. So applicability is really critical. Potentially even more peripheral is this analysis and assessment of some masonry arches. Now, masonry is surprisingly complex when compared to steel or even reinforced concrete, because it carries essentially no tension and relies on focusing compression down narrow lines. So I'm not going to go into any detail of what this is, but it's just another example of being able to develop a very complex analytical representation of something that behaves in a tricky way, and building up that belief that this can all be done. You just got to apply the right tools and the right processes to make it happen. And this does still today impact how I approach things in my work as a designer. And then finally, for the pre-design experience, I was part of a team that developed and documented a system called Resotec, which is a floor damping system, which basically works by removing shear studs from the ends of composite beams and then introducing a viscoelastic material in between. So this is the green line at the bottom center there. Again, I'm not going to go into the technical details of any of this, but later on in the talk, I'll be talking about the importance of and my input on footfall or walking-induced vibrations. And this early experience on quite a detailed technical level has really shaped and impacted the direction of my career, which we can see already in the next topic that's coming up. I meant to say actually earlier on that all of these projects I worked on the team. You know, none of these projects I did by myself, and I do feel extremely privileged to have been able to work with so many talented people through my career. And I'd say this is the primary reason why I've been able to gain the experience I have along the way. And later on, this is not just from other structural engineers, but also from the broader engineering teams, and then also from architectural collaborators through multiple projects. So enough about research and specialist analysis. You might be pleased to hear that this is now about design and construction and primarily buildings. This is the first project I worked on, and this was the Nichols Bridgeway at the Art Institute in Chicago. Some of you may well know the project and the bridge and have even walked across it and experienced it. The project director at Arup quickly identified some special engineering challenges on this project when Renzo Piano said he wanted the bridge to be like a blade flying through the air. This is one of the first architectural sketches indicating a depth of 2 foot to 5 feet for the 200-foot long span. In the end, it was actually even more slender at about 1.35 meter depth for a more than 60 meter span. And this was actually not too long after the Millennium Bridge in London, which was famous for its lateral wobble, lateral synchronous excitation. So bringing in specialist dynamics and footfall skills to the project was definitely the right approach. So jumping a little ahead, this is an image during construction that shows the southern half of the bridge. There's one support to the very far left in the image, and then there are 2 supports by the building itself, one by the cherry picker and another one just to the right of it. And then there's a roughly 15-meter cantilever, if I remember correctly. There was quite a funny moment in the architectural negotiations or discussions on this project, where after having successfully eliminated all the columns in this southern half of the bridge, the question came up can we now take out all the columns in the northern half? Unfortunately, I had to disappoint on that one, but very successful nonetheless. So in the end, the result, I would argue, certainly was a little bit blade-like. But how did we actually get there? So one of the architectural references for the design was a ship's hull. It was pretty clear early on that architecturally it was important that this was an expressed shell structure, not a great big girder or pair of girders clad with a shell. And given the proportions of the concept, it was pretty clear actually during bidding, tendering, where somebody proposed to do a clad solution instead, but that turned out to be completely unviable. So it can only work, the proportions are so squeezed, that can only work as a genuinely expressed structure. So having worked on ship hull analysis previously, this also became an engineering reference for me. And there are loads of parallels. Even if we use different design codes, the physics is often the same. Of course, not always. There's no wave impact on this bridge, at least I hope there isn't. But most of the physics is the same. And not only the physics, but also the analytical tools that we adopted were the same. All of this engineering was pretty familiar to me, and I could do this, but the ping pong with the architects and the concept of design as being an open-ended and open process was certainly new to me, and something I started enjoying. One of the tricky aspects of the structural design of this thin plate shell solution was establishing the buckling resistance for the free edges on these hulls. I don't know if I go back briefly to the other image, you can see on the section, the edges are completely free, and there is only a half pipe welded on to give it some local stability, but it's not fixed back to the main hull. So demonstrating the buckling resistance for this condition was pretty tricky, but with a shell plate analysis that I applied similar to the vessels in the North Sea, this becomes a pretty routine process. Now, if there's any structural engineering engineers on the call who can see a frequency number of 0.245 hertz, they're absolutely right that this has got nothing to do with the dynamic frequency, but if you multiply that with 2 pi, you get 1.54, which is the buckling load factor. So this is the output of a buckling analysis. So thin plate shell justification was one engineering challenge. The other was around the dynamics of a very slender footbridge, and this is dynamics and vibrations caused by normal walking. Even though at the time there was quite a lot of debate about the effect of running or groups of people walking and whether this could be more onerous. And as I mentioned, this was only a few years after the Millennium Bridge experience in London, where damping had to be retrofitted to the bridge to make it behave comfortably. So the long span slender bridge was always going to be low frequency, around 1.5 hertz, but the large modal mass of about 70 tons that we calculated demonstrated that the vibration should be well within the recommended limits. Now, I did mention debates around group effects and other scenarios, but in the end, it was pretty clear that the peak footfall was actually caused just by a single person walking, and actually walking at a pretty slow pace. What wasn't so clear was exactly how this would feel in practice. So it's a bit complicated, and it's the only graph that I'm going to show today. This is at high level meant to be a representation of a system to quantify the perception of vibrations or the tolerance of vibrations. So the kinked horizontal curves represent acceptability criteria in various circumstances, such as office floors at the top, indoor circulation spaces in the red, and then outdoor footbridges in the white. Oh, sorry, the other way. Yeah, that's right. No, the other way around. So I got that the other way around. I can't see the full image here. Outdoor footbridges is at the top, peaking at 10% G, and then indoor circulation, and then in white office spaces. Then the bottom dashed line is the threshold of perception. So the vertical axis is the magnitude of the vibrations or the accelerations, and the horizontal axis is the frequency of the vibration or the waves. So typical floors are often in the range of 4 to 8 hertz, which according to this guidance, published guidance, is also the area with the highest sensitivity. So higher frequency apparently are less sensitive, and according to this, also lower frequencies are less sensitive. We'll come back to this later, but the dot here represents, so the yellow and black dot represents the main span of the footbridge, which we can see is really a long way inside the outdoor bridge criteria, in fact, almost complying with office floors. But I've earlier presented this topic on bridge conferences, how I think the guidance and these curves are not necessarily representative of reality, and how this is perceived in practice can be pretty subjective and also very location dependent. Okay, another project. This is the Dubai Sports Complex, which is later on called the Hamdan Sports Complex in Dubai. It's a huge swimming arena with about 15,000 spectators, or 15,000 seats, which we designed with Faulkner Brown's architects. The project started in I think September, October 2008, with an intention to host the World Swimming Championships in 2010. So an incredibly ambitious design and construction program. This was also a time when there was massive construction demand and cost inflation. So one of the unusual challenges was having to order the structural steelwork during concept design. So pretty early on, we had to commit to all the primary steel sections, particularly for the long span roof, which we did. And then we did our best to try to keep those sections still working for these massive roof trusses as we went through detailed design. These trusses, by the way, are so big that you could drive a double-deck London bus through them, but I wouldn't recommend that you try. Going back to procurement decisions and ordering sections, of course, this is always going to be a risky approach, and the easy answer in such circumstances is being very conservative and just saying you need something bigger than what you hope. But the approach we took here was pretty different, because we if you're conservative early on, you'll never be able to make the savings later on, and you're going to build in inefficiency, which we didn't want to do. So we did it the other way around, possibly pretty naive, but we set a pretty high ambition, and then we had to pull out all the stops to stick with it. And largely we managed to do that. I'm not going to say much more about this project, just very briefly about how we achieved that tonnage target, and we managed to keep applying the sections. So one of the things we did was going from simply supported roof trusses to taking full continuity through the middle support, which is the kind of middle pair of pink concrete course there. This allowed us not just to make savings in the roof trusses, but also avoiding movement joints within the roof cladding itself. One of the key challenges on the project, I would say, was accommodating movements that resulted from the curved trusses and also curved girders that we had, both due to wind response, with the wind lifting and pushing down generated deflections on plan, and then of course also thermal expansion and contraction. So we had quite a complex system of bearings, including under each of the girders. And then we used the clear story window trusses that you can see all the way around to provide lateral torsional restraint to the girders. So normally I'd work pretty hard to avoid bearings and lock things together as much as I can. But on this project, that was unavoidable. So I thought, this is a 50,000 square meter arena with 2,000 ton steel trusses. Surely this is the biggest and the most complex thing I'm ever going to work on. But that wasn't quite the case. This is BBVA tower in Mexico City that we completed with Roger Sturck Harbour and Partners in London, and Legarreta in Mexico City. And on this project, I'd like to explore another aspect of the design approach and try to indicate how our experience might shape the outcomes of a project. This project was selected through a multidisciplinary design competition back in, I think, 2009. It's about 235 meters tall, and Mexico City is, of course, highly seismic location with very soft soil. Our team for the project had an experienced and strategic project director, but the main team, including myself, would maybe like to argue that we were generally analytically skilled and keen to get into this, but without much real high-rise or even seismic design experience. Seismic analysis was one thing, but seismic design, a different thing. Just very quickly showing the overall components of the project. This here is actually level 12, which is where the main lobby of the tower is. The tower is on the left, the kind of square, chamfered square on the bottom left. And as I say, the lobby is at level 12. So the lower 11 floors are primarily parking and a couple of MEP floors. So it's a very unusual configuration. There's also a 7-story basement in the full footprint, again, full of parking. On the to the right, there's an annex building, and that was all full of parking. But the top level of that had a cafeteria and was a pretty special open space, 12 stories up in a very exciting city. And then on the top, there is an auditorium, and underneath that, there is a helical vehicle circulation ramp. I think overall, there were about 2,500 parking spaces in this project, all of them required by code, which of course is drastically different from what you would do in a London project, where you'd be lucky if you could include about 25 spaces. So this was a sketch from the project director, Bob Lang, who was also very much my mentor in the sort of transition from analyst to engineering designer. This sketch was something he developed in the first couple of weeks, and this showed the strategic design direction with a perimeter steel frame and a core-less floor plate. I should have maybe mentioned earlier that the concept of having no structural core was fundamental to the whole approach for the vehicle circulation within the tower footprint, both in the basement and in the tower superstructure. So moving about a year or so ahead in time, this shows how the design evolved while all the principles were actually retained. So one thing that's maybe not so visible here is that the envelope was located inside this megaframe. So in between the floor plate, which is the kind of gray and red, and the megaframe, which is the blue. And of course, this generates all sorts of complications related to the seismic attachment of the floor plate to the megaframe, but also differential thermal effects and buildability considerations. But we applied our trusted analytical approaches and felt we could handle that. What's also maybe not so clear is the fact that there's only 6 perimeter columns on this project. So in each corner, there is a single column. So these are actually spaced at up to 35 meters. And on the interior side, there's a single column on the floor plate and then 3 rows of columns kind of next to where the lifts are, which isn't the structural core, but it's a central part of the floor plate. And on the bottom right, we can see one of the nodes in the corner, where the blue is the external mega frame concrete filled columns and braces, and then the red is kind of more conventional floor construction. So the image here on the left shows all the building components kind of in the right proportion. So the tower was only part of the story, and the tower was really defined and characterized by the mega frame. So the mega frame itself is an eccentric braced frame, a frame where the braces actually don't meet, which is something we'd always avoid. But in this case, we wanted to do. It's on a 3-story module, and that eccentricity allows for ductility or plastic deformation or distortion to happen within what we call the link or the yielding zone in the middle. So I'm going to talk more about ductility later on, but this is a sort of fundamental aspect of seismic design. So the floor plates, of course, don't span 35 meters. These are picked up by intermediate posts, which are then transferred out to the mega frame every 3 stories, and the load ultimately ends up in the big columns in the corners. And because this frame was external and eccentric and braced and on a mega level, and we couldn't find actually any precedent for this, we called it the world's first external eccentric braced mega frame. The seismic behavior of the link and the frame overall, of course, is critical. It's what's holding the building up. And when the deformation is focused into a relatively small number of small elements, it's crucial to fully evaluate the plastic deformation capacity that can happen in the link element. So we designed the frame so that this link actually could be removed and replaced in the event of a severe earthquake. And this is certainly a big part of the seismic resilience strategy, so that you can repair and reuse the building rather than to have to demolish and condemn the building after a large earthquake. This is something codes don't really pick up on, and it's something I'm not really going to go into on this talk today, but it's something that's starting to be much more understood and valued also by clients. Well, you can get into this in the questions potentially later on. Anyway, going back to the links, with the long duration earthquakes that we have in Mexico City, things like plastic fatigue is really a key design criterion, particularly for this design approach, and really to evaluate this in the level of detail that we needed to, I don't think we could have done without the close link between the specialist analytical support team and the kind of engineering design team that works with the architects. And at this point, I kind of was an engineering designer, but I wasn't so long ago an analyst supporting this kind of thing. So I kind of could straddle the 2 camps. One of the probably biggest challenges on the project was to get the transition from the steel superstructure and the mega columns into the foundations. So the foundations were built top down, and most of the load had to be transferred into diaphragm walls or slurry wall panels, which are basically disconnected. So getting a massive load from the columns at 35-meter spacing into essentially independent panels was pretty tricky. And we scratched our heads for a long time on this one. And in the end came up with a 2-story base plate in the form of a 10 by 10 meter, 50-ton node that was embedded in a 2-story capping beam, which ultimately could deliver the load where it needed to. But we certainly would think again of having this kind of column spacing on another project. One thing I found really quite interesting at the end of this project was how the structure became not just an integral part of the architecture, but also a leading element of the client image. Picture here shows, it was from the opening, and it shows the Mexican president speaking with the mega frame as a backdrop, which I thought was pretty exciting for a structural engineer. And then finally, it's difficult to see on this image, but this is taken from the ground floor, basically within what would have been the core. What I didn't mention earlier was that actually most of the lifts also only start at level 12, and there is a separate set of shuttle lifts that we can see on the left of the image that take everyone up to level 12, which is also where the security is. So the ground floor is basically completely transparent, which is pretty difficult to achieve in a tower in the seismic area. So this project had about 14,000 tons of steel, and I thought at this point, surely, it's not going to get any bigger and better than this. And in a way, I was right, even if I didn't think so at the time. So this is the Yongsan landmark tower in Seoul, in Korea, which I worked on with BBVA. And it's the middle tower here, the tallest building, which didn't get built. And normally I wouldn't speak about a project that either isn't completed or at least in the process of getting built. But this project had such big ambitions and so many unusual projects, and provides so many good examples relating to inquisitive or first principle design and also tall building efficiency. So it would have been 620 meters tall, and if completed at the time, would have been the world's second tallest building. So pretty exciting. So when dealing with a 620 meter tall building in the typhoon zone, the first and probably most critical job for a structural engineer is to advise on the massing and the aerodynamic sculpting of the building. This should really come ahead of talking about materials or systems or column spacing or any other aspect of the structural configuration. So this chart, of course, is overly simplified, but it's meant to indicate how a circular or well-rounded plan form reduces the drag or the along wind forces quite substantially compared to either a square or some other more angular plan form of the building. But in reality, actually on buildings like this, the wind loading is typically governed by dynamic wind response due to vortex shedding. And again, this is a function of the plan shape. And to establish this properly, even today, we still rely on physical wind testing rather than CFD like we see on the screen here. But vortex shedding and dynamic wind loading critically also relates to any changes in the plan shape over the height. So tapering form is always a great approach for tall, slender buildings, as consistent vortex shedding occurs only at a small part of the height at the same time. So when you've got a smaller diameter, it will vortex shed at a different wind speed. So therefore you only get a small proportion of the height acting at any one time. Now, I wish I could have taken credit for the massing solution that was taken forward on this project with a conical form and only a sort of slight slice taken into it, because it's super effective in reducing the wind loads. But I can't take that credit. The architects at BBVA came up with this themselves, and of course I eagerly supported it. The only potential improvement that I could identify even later on was that if we'd eliminated that cut or even rotated the building slightly, not catching the typhoon loads in the same way would have been quite helpful, because in Seoul, typhoons can only ever really arrive from one direction. So that could have made a small impact, but overall it was an incredibly good building massing. So having established the massing, the next thing is putting together the structure to resist the wind. And for super high-rise buildings, multiple outriggers is a pretty common solution. The system basically works to couple the core to the perimeter columns and transferring overturning from the core to the stiffer, widely spaced columns. And this typically happens over mechanical floors, so you wouldn't normally see or express any of this. And to get all the columns mobilized, often a belt truss, which is also shown here, is used. It can be quite a harsh system. You get massive shear reversal in the core, which the structural engineers can see on the green image here. And it can also be quite intrusive during construction, but overall the system works pretty well and it's tried and tested. The alternative approach, or one of the alternative approaches, is a full perimeter braced system. So this is where the diagonal braces are provided on the face of the building, and these mobilize the perimeter columns direct without any connection between the core and the perimeter. It's a pretty smooth system, but of course you do have to have all those braces, which are quite a strong element on the facade, and also cut across the floor plate. So with this system, the shear remains both in the core and in the perimeter, and there's limited exchange of forces, but it's pretty smooth and efficient and kind of clean system. But on this project, we decided we wanted to explore things further analytically without really having a particular solution or idea in mind. So it was a kind of open-ended process that we embarked on. And we played around with consolidating the braces in fewer areas. And in the end, we came up with something that was termed the helix bracing system. So this is essentially a discontinuous bracing system that only works in collaboration with the core, wouldn't work on its own. And it took us a pretty long time to figure out how it worked, much longer than it took us to understand that it would work. And in the end, we concluded it actually works as an indirect outrigger system, which is something else again, which I'm not going to go into. But indirect outrigger is normally pretty harsh, again, creating massive forces in the floor plates because you have to exchange big forces between the core and the perimeter columns. But because of the circular geometry of this project, with braces that go around an angle, change direction bit by bit, the force flow is very gradual. And again, the shear force diagram in the core, which is the green diagram here, shows how this is incredibly smooth and gradual, and I'd argue completely unique. I can't recall having seen anything like it on any other project or building system. So really quite bizarre. The other two, by the way, are the bending moments in the core, the red one, which is again smooth, but it normally is, and then the braces, the axial forces in the braces on the right. So again, just looking at how these helices are developed. So we got a double helix in each direction, each made up from a pair of braces. So there's actually still quite a lot of braces, but they are kind of focused in a very different way from a regular configuration. And then on the right here, actually, that's okay. So there was another curve that I forgot about. But on this one, you can see the proportion of shear in the core as a proportion of the total shear. So it never exceeds, never kind of gets amplified. And it's a kind of very gradual and smooth picture that means You don't have to design for any abrupt loads within the structure. So when we presented this at the time, we were trying to sort of make the point that the first step we took was to provide all the elements that support gravity. So the floor plates, the core, and the columns. And these all, form the kind of gravity system in the project. And then simply by adding the helix bracing, all these same elements then become coupled together and mobilize in order to carry the wind load together. So it's pretty unusual that even the floor plates contribute in this process. And because the force transfer is so distributed, they can actually do this implicitly without having to provide any additional material to do the job. So once you've designed it for gravity, stick in the helix braces and we can actually resist the wind pretty efficiently and stiffly. Of course, many other interesting stories on the project, such as the core stacking and even the core shape. We had a square core at one point, then a round core. And then also composite column design. So in this case, we used SRC columns, steel reinforced concrete columns. And of course, differential shortening and creep were major considerations on the project. One of the disadvantages of the tapering tower is that the location where the differential vertical movements, due to shortening and creep in the columns and the core, where those differential movements are the biggest is where the floor spans are the shortest. So not a very forgiving condition. So definitely needed a strategic approach to designing the system to limit differential vertical movements, which generally means trying to balance the stresses in the core and the columns so that they're kind of equally stressed, equally loaded. So very careful allocation of material to kind of all the vertical project components. So actually in the context of the creep and shortening, we identified that something like 40% of the column load in some of the columns was due to the weight of the column above. So the self-weight even of the columns becomes a pretty major driver on the structural design. So the other thing that therefore is super critical on the high rise like this is using really high strength concrete. And in this case, we managed to agree 120 MPa cylinder strength or 17 KSI for the Americans concrete strength with a contractor, which I've not been able to use since, I've got to say. But overall, the project was super efficient, about 90 kilograms of steel per meter squared, and about 0.45 meter cube per meter square of concrete, albeit, of course, very high strength concrete. Now, at the time, embodied carbon wasn't really in the vocabulary. Certainly wasn't a widespread discussion topic or design consideration. But then again, material efficiency and structural quantities have always been a big driver in high-rise buildings. So the two are pretty much linked. So if you do a very economical high-rise building, you're also likely to do a pretty low carbon one as well. So taking a break from the towers, this is a little project I worked on actually at a similar time to the landmark tower. This is Centro Botín in Santander, Spain, completely different scale. And the main challenge here was kind of the horizontal nature of the structure rather than the vertical nature. But throughout the project, there was immense attention to detail in the design of the numerous expressed structural elements. And some really quite huge cantilevers. I think 24-meter cantilever, if I remember correctly. And of course, the whole building raised off the ground, apparently pretty effortlessly. So not only do we need to fight gravity, but we also need to make it look easy, even of course, if it isn't. And then of course, minimum columns and minimum stability, minimum size of stability elements between the ground and the elevated volume. In fact, on this project, we used some steel tubes around mechanical risers as the only main stability element. So you can kind of see in the middle of the picture under the screen, in between the two columns, one of these cylinders, which is how we stabilize the building. So pretty finely tuned design for this. And the building also extends a long way over the sea. So buildability of this was, of course, a pretty complex and unique additional challenge on the project. Just another picture. So at the opening of this, one of the partners at RPBW actually commented on that the columns look too thin, which I wasn't quite sure how to interpret, but I chose to take it as a compliment. Of course, gravity still does exist in Santander, and the design only works because of substantial and pretty complex structure that's embedded and hidden mostly from view. So really quite close collaboration between the architect and engineer was needed to make something like this viable, because not only do you need the structure, but you need it in the right place, and you need it to fit in with the architecture, or you need the architecture to fit in with the structure. Take your pick, but it's give and take and ping pong along the way to make it happen. But what I actually really wanted to talk about on this project was some of the elevated and suspended circulation structure or kind of deck that's shown in this image. This deck is located between kind of two buildings, or two halves of a building, and it forms a kind of piazza, but also a series of observation decks, and also forms part of the egress and access system. And because all these walkways have an absolute minimum amount of vertical support, so even where we have hangars, these only attach to one side, typically the inside of these passerelles. So incredibly challenging to get the dynamics to work out on something like this. Here's an image from below, of course, glass floor, but also you might notice no columns. So really quite slender, long spans, and very, very few columns. And this shows the overall building cantilevering over the sea, and also indicates on the kind of to the left in the picture a 9-meter long trampoline, as we called it at the time, that extends out from this. So unlike the bridge in Chicago, this one here, this trampoline is both light and pretty flexible. So it's pretty difficult to get something within the 600 millimeter structural zone, expressed structural zone, to cantilever 9 meters out, particularly if it's supported off a very flexible point on the building. And because it's over the sea, the perception of these vibrations could also be interpreted pretty onerously. You might feel not particularly sort of reassured or safe if you can perceive the vibrations too significantly. So we thought the only way to kind of be clear on what we thought the criteria were on this was by doing some mock-ups of the condition. So this one shows the undamped configuration. So this was a kind of structural mock-up that was meant to represent the dynamic properties correctly. So a single person could get this moving quite dramatically. You can probably hear that noise in the background. We then went along and looked at what happened if you had more people, and this was of course, an absolute disaster. The kind of vandal design condition was pretty difficult. You didn't need 10 people, but if you did put 10 people on it, we're pretty worried you could scare people and also potentially damage the structure. So early on, we knew we needed to damp this platform, this trampoline. So here is an example of one of the configurations of how this behaves with the damper. So instead of the structure moving, you kind of you focus the movement within the damper itself. But there were, there were a couple of challenges with this, and we also struggled to make it fit within the girders, within the structural zone of the project. But overall, we thought it could work. However, if you really wanted to, we then identified that you could actually exceed the stroke of this thing. So it wasn't quite there. We needed to do something else. So we went back and managed to get a little bit more stiffness within the structure. And by doing that, increasing the frequency, the tuning of the damper worked much better, and we could actually use the same damper in the permanent condition. And because the damper, of course, looks so great, the architects decided that this should actually be expressed. And this was a pretty unusual and rare opportunity to be able to express some of the advanced structural kind of behavior, or complex structural behavior within the design, expressing that architecturally. Really quite special and exciting. And here's another picture showing a big group of people standing at the tip of this, and I'm pretty sure they would not be there, or if they were, they wouldn't be very happy if we didn't have the damper doing its job underneath. So going back to the plot again, so this now shows the long cantilever, the trampoline in the middle there, as well as two kind of shorter, smaller cantilevers kind of in the middle and to the right. These are higher frequency, and it's pretty clear to me that these are much less critical in terms of perception. But I'm pretty clear that we can't just follow published guidance on this, particularly at low frequencies. I think the vibrations can be perceived more like movement or displacement rather than vibration or acceleration, which is very different from high frequencies, where eventually this becomes sound. You can almost hear it up at sort of 30 or 40 hertz. You can hear it. So the kind of dashed blue line I put on here is it's not a serious suggestion. It's a bit of a provocation, but I think it's potentially as correct as the kind of kinking back up default condition that everyone follows. I think the key is that this can really be subjective and really location dependent. So you can't just follow code, basically. So back to towers and tall buildings. This is A25, or often referred to as Fubon Tower in Taipei, Taiwan. This too is with Renzo Piano Building Workshop. Currently under construction. It's topped out, it's mostly clad, and it's due to complete later this year. 265 meters tall and relatively slender. Some of the key architectural aspirations here were transparency, both in relation to the facade and to the structure, and both of which I'd say are pretty successful. I'm not going to talk about facades today, but I will talk a bit about the structure. Having learned from BBVA that the column spacing of 35 meters doesn't make our life particularly easy, here we did the complete opposite, went for a really close column spacing of 5.8 meters. And this wasn't just to make the foundation interface more bearable, but it also was related to the approach we took, which followed the code framework in Taiwan more closely than we did in Mexico City, which was more a performance-based seismic design. But unlike Mexico City, Taipei is exposed to typhoons pretty regularly. And on top of that, it is also highly seismic and has very soft soil. So you got all the challenges happening at the same time. So given the height and the slenderness and environmental demands, it was pretty clear to me early on that we needed to mobilize the perimeter columns to resist the wind loading and the seismic load. And because the perimeter columns are so much more effective in resisting overturning, we decided here too that there wasn't really much value in trying to use the core for anything. So that was all pretty clear. Now, what's the plane about? Here I'm trying to convey the wind forces that act on the building during a super typhoon. And it isn't actually equivalent to a single A380 pulling on the building. It's actually more like this, equivalent to 63 A380s at full takeoff thrust, all pulling on the building. And this is in the design wind condition for the project after all the wind sculpting. So nowhere near the kind of worst case scenario of what it actually could have been. And also during earthquakes, the internal forces that generate in the system are even greater. And I'll explain that a little bit in a minute. So even though we had here 24 perimeter columns, as opposed to the 6 perimeter columns at BBVA in Mexico City, the peak load here was actually over 70% of the BBVA column loads. And we actually had much higher tension in the columns than we had on BBVA. And that's due to this incredible overturning effect, which originates primarily from the wind. So again, absolutely critical to integrate a robust transition from the superstructure through the basement into the foundation. So we take nearly 20,000 tons of compression force in the columns and 10,000 ton tension force in the columns. And the ground here, looking at it, the closest similarity I can think of is it's kind of black toothpaste. It's so soft, it kind of falls away. And this is what you're trying to sort of provide foundations for, to resist these immense forces. So all the structure, of course, comes at a great cost. So we need to use all the tools and all the ideas to minimize the loads and the structure. And in structural design, ductility is one of these tools that we use. So ductility basically means to allow something to deform in a controlled manner, which means we can design for smaller kind of overall forces. The opposite of ductile is brittle. So a glass building, like the image on the left, is pretty strong and stiff, but once you exceed the capacity in it, it will fail catastrophically and basically explode. While the steel tube, on the other hand, you can imagine that bending and deforming while still resisting some load, even if it is weaker and more flexible initially. And same can apply to concrete. These are some images that are borrowed. One of them shows a brittle concrete failure in shear, and the other one shows a ductile concrete failure in bending. So it all depends on the configuration and the reinforcement and how we make the elements resist the loads. So for a building system, the most ductile system we have is what we call BRBs, buckling restrained braces. And these, when combined with ductile moment frames, allow us the maximum code sort of force reduction factor of most ductile design. So these BRBs, I'm not going to go into it now, but basically it's sort of a truss within the truss, or it's an element that the central gray element is allowed to yield and deform in a controlled manner, both in tension and in compression, because the outer casing, the red casing, restrains it from buckling, hence the buckling restrained braces. So on this project, we managed to integrate and to develop the largest BRBs ever, actually about 2/3 larger than the largest reference project we could find. And even so, we still needed double BRBs in pairs. So absolutely immense forces on this project. But why were the demands so crucifying on this project? I mean, it's a relatively moderate sized tower, 265 meter tall and 42 meter footprint. So we really wanted to get to the bottom of why the demands were so difficult to manage on this. So we embarked actually on a research project to fully understand the interaction between wind and seismic demands on this tower and towers generally. So if you have only seismic loading, like on BBVA, you design the ductile elements or the link, little link in that project, or the BRBs on this project for the seismic demand. And then you design all the other elements for what we call an overstrength demand. So basically a sort of slightly amplified demand, which allows us to make sure that we capture the upper band forces that happen in the ductile system, and then all the other parts of the project remain elastic and don't get damaged or deformed or yielded in that condition. But if the basic wind demand is higher than the seismic demand, then this approach isn't valid. And the reason for that is that we need to design the ductile elements to resist the wind loading too. So we need to increase the capacity of those. So for the A25 viewpoint tower, the braces needed to be increased to design to resist the wind loading. But then if a large earthquake come along, these can then yield and strain harden the BRBs so that the columns and the foundations experience, again, an amplified loading from that in turn. So these are kind of additive effects, and we need to design for all of this, of course. So for those that are particularly interested, we published a paper on the generalized interaction of wind and seismic loading on tall buildings, and this is freely available to download. As a very, very brief summary, we identified basically kind of 4 zones of wind seismic interactions. So you can either have purely seismic governed like BBVA and Atrio, which I'll show in a minute. Wind plays no effect. And then you can have a purely wind governed project like Yongsan, even if Seoul is somewhat seismic, that had no impact on the Yongsan. Or you can have the case where both wind and seismic interact and governed, like on A25. And in that case, we fall onto what we call the ridge of despair, where they are in effect additive. And they aren't additive because they happen at the same time, but they both increase the demands in the structural elements. I'm just looking at the time here. So moving on, almost done. Just one brief kind of topic shown through a couple of projects. This is on the left here is Atrio in Bogota in Colombia, and Chapultepec Uno or R509 in Mexico City. This one actually is literally across the road from BBVA in Mexico City. I had less involvement on these 2 projects, but there's a couple of things that I thought I should bring into the discussion nonetheless. Atrio was unusual in that there was a huge cost and skill difference between steel and concrete in Bogota. So we aimed to use concrete wherever we could, and then steel only where we absolutely had to. So in this case, we actually did have a concrete core, and we used steel reinforced columns. But the braces were steel, and these are ductile special concentric braces, SCBFs. But unusually, they're on a 2-story module, not a single-story module. R509 is super slender, 245 meters tall, and only 25 meters wide at the base, and again on very soft ground. So on this one, we used soil structure interaction to take advantage of the 12-story deep, stiff basement to reduce the seismic loading. This one too, of course, had an enormous amount of car parking, including both in the basement levels as well as the tower superstructure. So pretty unusual. But common for both these projects is that we used multi-story special concentric braces. On Atrio, there were 2-story configuration, and on Chapultepec R509 on a 3-story module. So we used multi-story braces simply because they're more efficient for a sensible column spacing. And I'm not talking about 35 meters or even 5 meters, but say 9 meters, single story braces are too flat. And there's also too many connections. The image on the left kind of indicates the size of the connections. So chevron braces, like second from left on top, is of course possible, and this corrects the angle, but we still have loads of connections. And with ductile braces, you also have to take an out of balance vertical load in that chevron configuration, and this can be a pretty big deal. So it's essential that we get as similar as we can tension and compression capacity of the braces. So BRBs do this well, but other braces typically don't do it so well. So we wanted to take restraint at each floor level for the braces to make the braces stocky and to have a similar tension and compression capacity, and also just a high efficiency of the braces overall. But we needed to demonstrate that the braces buckle in a consistent way in each story, like shown on the left in the idealized configuration, and didn't simply sort of buckle in a single story, which shows on the right-hand image there. And this was particularly important in Mexico City, where we had very long duration earthquakes with many cycles. So we need to control the plastic strain that happens in the braces and actually spread it out as much as we can. And we were pretty surprised when we couldn't find anything published on this technically, because we thought this is something you'd always want to do. So again, we did our own research. We combined advanced analytical approaches together with published experimental data. So we didn't do any of our own physical testing, but we could adjust the analytical approach to kind of match the published data for physical testing. So the image on the left here shows a post-buckled condition of the braces. So these braces are designed to buckle, but here they're kind of shown in a spent condition. So the pink color in the plots shows where the plastic strain capacity is exceeded due to plastic fatigue, and the material starts cracking, which is what you can see on the photo on the left. This research allowed us to successfully establish the parameters that kind of govern this multi-story approach, basically getting each of the spans to contribute and to distribute the strain. And the impact on this design, or the impact of this on the building design and the efficiency of the building was pretty significant. And because of the novelty of this and the impact, we made sure this was peer reviewed, which was, a fruitful and constructive approach. So there's loads more to say again on this topic. But I could refer you to this paper, which is actually pretty easy reading compared to the wind seismic interaction one, which is pretty heavy going. So getting to the end now, wanted to kind of share some of the general approaches that we've picked up through the many projects where we've been working hard to achieve efficient, low carbon, tall building design. So I haven't talked about all of these in detail, and some of these are quite technical, but other ones are, important also for architects. So the first step is to limit the demands. So if it's a wind governed project, you've got to get the wind sculpting and the massing right in high wind areas. Not too slender project, and ideally tapering the project. If it's predominantly a seismic area, limiting the weight is it's the most effective tool to limit demands. Then also soil structure interaction. Then using the full footprint to resist the overturning. So mobilize columns, all the perimeter columns. It's pretty much always more efficient, and there's many ways of doing it. Outriggers, braces, preferably not a moment frame. Those are always less efficient, but very ductile. So maybe in combination with something else. Then mobilization of all material. What I mean here is once you've provided all the material for gravity, then use it for lateral resistance. So the reference here is Yongsan, the core and Yongsan, you know, it's already there. Let's use it also for overturning. And then this is a key one, not deflection controlled, proportion of building, so that when you size all the elements for strength, they also meet deflection criteria. Sometimes you need to push these criteria because we really don't want to add material for stiffness. There's got to be a better way. Direct load pass, this is pretty key. Any transfer in a tall building is wasteful. Axial load paths are typically better. So braces rather than moment frames when you can, you know, get forces like to go in a straight line, but you know, you can kink them slightly, but try not to rely too heavily on bending, other than, of course, in the floor plate. And then using the material in the most efficient way. So the key here is, you know, is it a compression demand or is it a tension demand? If it's predominantly compression, concrete is lower carbon, lower cost typically, but sometimes columns go into both. On A25, we had, you know, immense tension in the columns. And on a super tall, super high-rise project, the weight of the columns themselves might become a key driver. So, you know, you can't fully generalize these things, but typically using the material in the most appropriate way is generally best. Finely tuned systems. So this is about investing the time in really tuning everything. So avoiding differences between tension and compression resistance in the braces, reducing the overstrength that applies in the ductile system, and then increasing sizes can actually be unconservative. So if you've got a brace in the building and you decide just to rationalize these, make them all the same, you really need to design the columns for larger loads than if you optimize all the braces. So, and you know, it's not always that straightforward or that obvious. Performance-based seismic design. So where this is possible and where the codes allow you to, you can use performance-based design rather than sort of simplified code design. Code design really isn't written for tall buildings, at least typically they aren't. And first principles approaches generally are better and allow you to get a more efficient building that can perform better. But you typically need to adopt, of course, the spirit of the code and the kind of intentions of the code, even if you don't sort of follow them quite to the letter. And where you have a stiff basement in soft soil, look to use soil structure interaction. This can really quite drastically reduce your seismic loads in the building. And then finally, and I didn't talk about this today, but where we fail with the wind sculpting, the second best approach is then to provide structural damping within the building to not just improve the comfort and the dynamic wind response, but also to reduce the dynamic wind loading. So I know I'm probably gone over time here, but so those are kind of 10 key steps for efficient tall building design. So hopefully I've been able to also demonstrate some of the kind of value of explorative first principle designs, relying on physics, maths, and advanced analysis rather than necessarily precedent or co-design. So on that note, I'd like again to thank you for the opportunity and head over to the questions and the discussion.
William, thank you very much. That was an incredible presentation. Technical approaches and advanced analytical methods. We were all trying to figure out how that was going to work out in your title, Challenging Convention and Inquisitive Structural Design Ideology. Now we've figured it out. And you know, the examples that you showed were fantastic examples from your research and how the research played into the different examples. So that was a great presentation. Thank you for that. We have about 30 minutes left, and we have 5 people that we've asked to prepare some questions. And I'm going to ask each of them to come on individually, and I'm going to ask them to do just one question each, because I think we have quite a few questions from the audience as well. So I'm going to ask Ross Park to come on first. Ross is an architect from our Glasgow NORR office. Ross, you have a question for William.
Yes, thanks. Hi, William. Great presentation. From a sustainability point of view, you obviously talked about some aspects of that through the presentation, but with buildings now looking to meet low to zero carbon targets, how as engineers do you incorporate that into the structural design in terms of whole life carbon assessments and for the materials that you use in the structure? How is that kind of captured in the whole design process for the structures of these kind of mega structures?
Yeah, so it's pretty integral to the design, and of course not just the structural design. I'll probably focus mostly on the structural design in my response, but you know, nowadays we calculate the embodied carbon of all our projects, not just the tall buildings or the kind of mega projects, but all projects. And we also develop a kind of low carbon strategy for projects as a matter of routine, I would say at this stage. So along with a kind of strategy for an efficient and well-performing and resilient and robust structure, you know, we also have implicitly a strong focus on a low carbon solution. So on some projects, we also like to try to sort of set a carbon budget. So, you know, what is kind of typical best practice on a project like this, and then how can we improve on that, and what sort of level of ambition, you know, should we set ourselves for achieving that? So should we try to get to 50% of business as usual, or, you know, can we do even better, or, you know, can't that be achieved? And this needs, to realize these things, we need a very strong and collaborative dialogue with the architects, because as the point I've been making, you know, you can't do an efficient structure without the right massing for a tall building. So you need, in a way, you kind of need to do everything right. So you need to be able to agree on a sensible proportion. You need to try to get the wind sculpting right. And of course, you need to do all the usual things with cement replacement and you know, minimize quantities where you can. But I think what I would say is that, you know, where we are today is that we can get, you know, maybe towards sort of 50% of business as usual, or, you know, best practice. I think the question is, how do we make the kind of next leaps from that? And I think some of these will have to come on the material front. You know, what's the kind of, so we can't just rely on cement replacements, GGBS and PFA, you know, those are kind of limited resources, and actually there's a lot of demand for them. So we need to continue making improvements in other structural materials. And I'm not talking necessarily about timber here, but also what's the kind of next generation of low carbon steel, next generation of low carbon cement and concrete. These are the things that will become really important as we move forward. There's probably other people who are better placed to talk about operational carbon and, you know, whole life carbon than me, but again, it's something as a design team, you know, we do as a matter of course on our projects these days.
Thanks, Ross. Thanks, William. So I'm going to move to one of our structural engineers, Adrian Chodiela, from who's a principal in our Calgary office. Adrian.
Hi, William. Impressive work and an excellent summary at the end there. Thank you for the presentation. I like how you highlighted the dichotomy between our ability to calculate most things, as you put it, and the feel in practice. It only proves one more time that while in theory there's no difference between theory and practice, I guess in practice there is. So while we rationally understand that strength, stability, and serviceability govern the design of the built environment, for both objective and subjective reasons, what would make it possible to achieve 100% utilization in structural design and increase risk acceptance on the client side, at least on the serviceability aspect, as you put it, push the criteria?
Yeah, I think, again, there's many facets to this, and, deflections, I could talk a lot about deflection limits in tall buildings, which is probably a stronger driver than comfort limits. In China, it's routine to design for height over 800, which kind of crazily, stiff requirement.
Yeah.
In London, maybe height over 500 or possibly 360. But in Fubon Tower in Taiwan, it's designed for height over 200. So because they get these kind of horrendous typhoons, you acknowledge that, you can't really try, that there isn't a need to design the building to be stiff enough not to deflect more than a few hundred mil. There's actually nothing wrong with it moving half a meter, in that scenario, or more. Facades can be designed to accommodate this. So I think there is work that needs to be done to, within the overall industry to be able to accept larger limits, because what we want is for our projects to be strength controlled, not stiffness controlled. And, very often that is possible simply through the configuration of the building. So if you've got a tall, slender building, it will be very difficult. If it's a sufficiently stocky building, you can sometimes meet the deflection limits implicitly. So A25 Fubon Tower, for example, deflections didn't govern anything on that project, nor did wind vibrations, because we provided comfort damping at the top of the building. So on that project, we didn't use damping to reduce the loads, but we did use them to reduce the perception of loads, which in my view was probably not really necessary, because it's not a residential building. And if there's a typhoon, you're not going to be hanging about in your office at the top floor of the building. So it's a bit different for residential buildings. But yeah, I think you're right that we need to do more on this. And the more we can increase the understanding that people have, I think that the further we can get. So taking clients to perception mock-ups is one approach. So we have actually in New York and in London, we have a motion platform where you can make people sit down and then experience vibrations at different levels and identify if we think those are tolerable or not. So you can try to take people with you rather than necessarily sort of trying to change the rule book. You can convince rather than change the rules.
Thank you.
Thanks, Adrian. And we'll move back to an architect, Mark Van Werder from our Detroit office.
Hi, William. Thanks. That was a great presentation. Thanks. Looking at the buildings that you chose to present, see a lot of expressed structure. Makes sense. But we all know that not all buildings have that expressed structure. Can you give us an idea of maybe how your approach to a project changes between, say, one that's got expressed structure and one that we might call the structure is shrouded in mystery? Right?
So I'm not sure it really does change so much my approach. I would like to think that good architects will want to express the right structure, or the sensible, or the efficient, or the kind of logical structure. You want to be able to see the load paths. So I'm not sure there is a fundamental difference. I mean, of course, there are differences in how you treat, fire protection and corrosion protection and, thermal response and kind of these technical things. But I'm not sure my design ideology, would be particularly different for a project if I didn't know whether or not an architect was planning to express the structure, and I kind of saw this problem arrive, and I sit down and think, how do I solve it? I think I would probably give the same answer in both cases. But of course, it's always easier when you can hide things, particularly connections and, all of these things. So it is an extra challenge to express the structure. And at the same time, I do also kind of feel it's a bit of a privilege to be able to show off the structural engineering as a part of the architecture and potentially as part of the client's image. But I do projects where it's covered up as well, and that's okay as well. And on projects like Centro Botín and Santander, actually most of the kind of really interesting and challenging structure was hidden. Right, what you see is only a small part of it. So they, often they need to work together. The express structure on that one would only work because of the kind of restraint and the support it got from the hidden structure.
Great, thank you, Mark. So we'll move to our structural engineer Hassan Safarini, principal in the Toronto office.
Yeah, thank you very much, William. That was absolutely exciting, very impressive. I really have a ton of questions that I'd love to ask you, but I can see
you should get in touch.
Already staring at me
later.
Yeah, absolutely. So I had one question actually from a presentation that I have seen from that you'd given the Institute of Structural Engineers about adaptable structures rather. And you had alluded to your results in your answer to Adrian, and basically we're getting a lot of clients, major clients actually, who come asking about checking facades for seismic anchors, and reality is wind is far more the out of plane inertia is really a fraction of the out of plane pressures of wind, and the other thing, which is the drift implications and so on. As you had said, I mean, our current codes are much more conservative than others, like in Taipei and so on. So if we only can verify that those buildings do comply with those drift limitations, wouldn't that just automatically kind of allay those concerns of really needing to worry about seismic, just because seismic was not there in 60, 70 years ago when the original designer had conceived of the building and the structure?
Yeah. Well, so I think a couple of things I would say to that, and just going back to the drift limits and the facade design, in this case, having a strong relationship with a facade consultant, whether it's internal or external on your project, you need to, the more we can kind of share what the real limitations are and where the increased costs or increased material intensity or, movement capacity, you need to strike the balance. So if you could accept, a few millimeters bigger joint in the facades architecturally and for the facade consultant, then, if you can save 2,000 tons of steel, that's a discussion that we need to have. It's not a discussion that should be taken for us. It's a discussion that everyone should be part of, and we can kind of jointly then agree what we think is the right solution and the right approach. So going back to seismic demands on facade, I mean, this is an area where there isn't always such a good understanding, and maybe it's partly for historical reasons. There's a lot of conservatism around, but I think it's a question of robustness as much as it is of deflection limits. You know, how much can the system accommodate in terms of unexpected deflections, unexpected movements out of plane, in plane? What is the failure mode? Does something bend? Do you tear a silicon joint, or do you bend a molding, or do you get a breakage and facade panels falling out? I think there isn't an answer that kind of determines the best approach for all of these. And I think the complexity is then often in existing buildings where it's difficult to actually understand how everything is fixed together, how much it can really take. But when it is a new project, I think you have control of these things, and we can try to work together to strike the best overall, overall balance on the design drivers. I know that probably wasn't such a clear answer, but yeah.
Thank you very much. We can chat later perhaps on this and other issues, but let's see
absolutely.
you move on.
You can call later, Hassan.
Yeah.
Thank you. And our last question comes from Antoine Chaya, a partner at RPBW Paris office. Antoine.
Thank you, William, for this extensive presentation. It's always a pleasure listening to you. The structure of the building does not come to save its architecture. It's not supposed to come to save the architecture, but it's an integral part of its storytelling and its semantic. The dialogue in between is fundamental to the consistency, the clarity, and the integrity of the whole scheme. How do you qualify the working relationship, the ping pong between engineer and architect?
How do I qualify it? Or...
Yeah, I mean, also based on your experience, how we work together and how you can describe, because I heard a similar question, but was not.
Well, it's taken me 15 years to sort of try to figure out, how to work with you guys. And, sometimes it's easier than others. But what I find, because you're absolutely right. I mean, the dialogue and the constructive environment and the kind of mutual trust, of course, are fundamental for this. So one of the things, two things actually, I find really sort of critical in this process. One is to be able to do it quickly. Architects are impatient, right? So if you ask me for something, I can't take it away and say I'll get back to you next week, with a column size, being able to give an approximate answer kind of off the cuff and just try to perceive how this can work together and then do some very rough numbers, is often better than doing a very detailed and sort of fully developed response later on. That's one thing, but also then taking the time to explain what the structure is really trying to do. I do find that you guys actually listen and are interested, and some architects are more interested than others. But generally, if we take the time to explain what the engineering is trying to do and what the structure is going to do, same applies to glazing and solar gains and all of these things. If we explain what really matters, we do our homework and convey it in a way that is understandable, then I find that you guys are pretty interested and open-minded and often embrace the engineering.
Thank you.
Thank you, Antoine. Kevin, if you want to come on, I think we have some questions from the audience, and Kevin is going to host those questions.
Right.
Yeah, thanks, William. Yeah, a very interesting lecture. Lots of very positive comments. You'll be pleased to hear. Lots of tricky engineering questions that as an architect I don't quite understand, but I'll ask you some of those. But there's an interesting one here from John. I mean, you talked there a little bit about the process, and you know, the way technology has advanced in recent years, you know, with building information modeling, and almost kind of any form is achievable, isn't it? But in terms of the process of how you design the building, I thought it was interesting. Your colleague, you showed a sort of freehand sketch of one of your buildings early on, which was actually very nice to see. But there's obviously close collaboration required. So there's two or three questions around that, you know, how the process works. And there's one specifically that's asking if you can give an example of a sort of challenge and a compromise between the logical process that you want to go through, I guess, and the intuitive process that the architect might want to go through.
Yeah, okay. Yeah, I think I can relate to that. I mean, in terms of the process, so that hand sketch from Bob, that was, you know, to me, that was sort of to convey the importance of the strategy, having a clear view on what we think is right and how it should work or could work to give us the right result from an engineering perspective. You know, it shouldn't be, you know, it should absolutely not be the situation where the architect does his work, then says to the engineer, here, can you stick some structure on that? And of course, that's, you know, that's not an approach I can really relate to it at all. But, you know, I know that it still exists, unfortunately, but that's what kind of not to do. In terms of compromise, you know, every job is a compromise. You know, design is about compromise. So, you know, it's about getting the right and the kind of balanced compromise. An example of this, I would say, is the Fubon Tower, the A25 tower, which, you know, has kind of notched corners, which does an awful lot to reduce the wind loading. You know, so that was agreed, very helpful, you know, has a big impact both on the positive impact on the architecture, but also positive impact on the structural design. However, having the kind of tall screens, which are absolutely integral to the architecture, but not integral to the engineering and not helpful to the engineering, that I would say is a, you know, is a kind of balanced compromise where, you know, you accommodate something within the design that isn't ideal, because you've done everything else. You've come a very long way with the rest of the design, where you can afford to accommodate something like that and still be super efficient. I mean, the A25 project has about 30% less steel than the typical benchmark in Taipei for even brand new buildings. You know, are much heavier than this one. And the reason for that is the approach with the braces, the way the columns are spaced, and everything else. So we can accommodate the glazed screens at the top of the building and still meet you know, incredibly competitive material quantities. But yeah, every job is a compromise.
Yeah, you know, sublime compromise. Yeah. Just as a quick addendum to that, in terms of technology, again, it was interesting to see that despite all the incredible things that digital technology and computer software can do, you still build models in wind tunnels. Yeah,
we still rely. Wind. So we don't generally do this ourselves. You know, we use wind tunnel laboratories to establish the, you know, the final wind loading, even the cladding pressures. You know, we use wind tunnel analysis. Wind is such a you know, such an unpredictable system, such a complex system that you know, that's still the best way to do it.
Yeah, interesting. It's kind of similar in car design, almost, isn't it? Yeah. Jamie asked the question about, you touched on the square plan form in the A25 tower, and I think they're just curious about, you know, that the analytical diagram initially showed a circular form. So you mentioned that the corners help with the wind resistance, but was there another architectural reason as well that you finally adopted the square form in reference to other possibilities?
On that project, it was actually a client driver. We we actually initially had a circular planform on the project, which
Clients.
had to be revised for one reason or another. I mean, of course, there are some challenges with circular planforms, particularly if it's a relatively small diameter. Putting an interior layout, desk layout. Desks aren't circular or like semicircular. So, nor are ceiling panels or floor tiles. So there are some reasons, why it isn't ideal. But yeah, as I say, putting those notched corners in, I would say reduce the wind loads by something like 25% compared to a pure square extrusion, which would equate to, of the order of 4,000 tons of steel. So it's, these are, projects like this in that kind of wind loading and for these proportions, these are big decisions that you need to get right early on, because nobody's going to thank you. When you're in schematic design and you've done your wind tunnel test and you think, oh yeah, wouldn't it be great to, to have a round building instead of a square one? That boat is gone, right?
Yeah, and I think that's why it's really important that architects and engineers work collaboratively, don't they? Because certainly in my experience, the best engineers always contribute to the architecture. It's definitely an evolution. I'll ask a technical question now, so you need to bear with me. But so Tarana asks about the BBVA Bancomer project. He said you mentioned the replaceability of the EBMF links. What sort of details did you incorporate to facilitate replaceability, or was there a replacement protocol that you may have developed?
So okay, that's a pretty knowledgeable and good question.
That's what I thought as well.
Yeah, and I didn't elaborate on that. Now the reality is, because this link element, is designed to be able to undergo these kind of enormous amounts of deformation. You can't simply cut out that piece and then weld in a new piece, because then the welds would be in the most critical locations of the project. So you would need to actually replace a link piece together with a stub of the kind of horizontal beam and the two diagonal beams. And this was how it was also installed during construction. So there was a kind of much larger piece rather than the 2.5 meter link. There was maybe roughly a 5 meter piece which comprised the links and the stubs, and you could then make the welds in the areas that are not undergoing this plastic deformation. So that's how it would also be done in the replacement scenario. But the other thing I didn't elaborate on is the fact that here there was a massive advantage of the frame being independent of the floor plate and outside the facade. You could actually leave the facade, leave the floor, even leave the desks kind of where they are, and then you could replace this link from the outside of the building, which is fundamentally different from, for example, a moment frame building where you're relying on all the steel beams that also support the floor. You rely on those to then resist the seismic loading. So if the building deforms, everything in the building is kind of damaged, and you can't cut out a piece and replace it because it's so kind of endemic and widespread in the building.
Interesting. Yeah. There's another another engineering question, just conscious of time. I think we're almost there, from Ahmed. Can you elaborate on how you calibrated the brace behavior with the published experiments?
Yeah, I can. And it's funny, I have a slide on that didn't make the final cut. But we did some pretty detailed curve fitting. So what we did was we analyzed the behavior of a strut, not one that we had in the project, but one that had been tested experimentally, and there was loads of data. So we kind of replicated the physical experiment computationally, and then we tried to fit our results to match those. And you can look at what's called hysteretic curves, the stress strain curves, or force deformation curves, which we did. And pretty sure a lot of that's in the paper that we published. So I would encourage those who are interested to take a look at that, because it was really quite interesting, that approach. And the results were, surprisingly aligned, much better than we had anticipated. So it was really quite an interesting exercise. So worth digging out for those who work in that kind of field.
Great. Maybe time for one final question. So
Yes, sir. Yeah, go ahead.
David Cluzio was asking, but obviously in the sort of low carbon environment that we're working in, have you had any involvement with mass timber, or have you considered, mass timber structure for some of the projects they've worked on?
So I'm working on, and unfortunately I can't share any details of this, but I'm currently working on what will be the largest mass timber application on any project in the world, with up to more than 2 by 2 meter timber columns, and then a long span composite steel CLT floor. So yes, and it's also high rise, well, moderately high rise.
How tall is it?
It's 100 meters, but it isn't timber. It isn't timber all the way, and it's very challenging. And there's a lot of excitement around mass timber, but there's also a lot of challenges. And it'd be great to come back and talk about that project in a few years when it's developed and built. But yeah, it is a subject that we're working on many projects. But the tricky thing is, how do you achieve better efficiency? So if you have to clad all the timber, fire protection, you have to have spans that you can cope with timber. There's many limitations. So you need to work, again, this concept of finding the right compromise is even more important, I would say, in the timber building.
On William, since we're at the end, I won't ask you a skill testing question, but I do want to pick up on something that was talked about a little bit earlier about relationships between architects and engineers. And if I go back to the very beginning of the presentation, I put that slide in there very intentionally, the one with, the quote from Walter Gropius about architecture begins after engineering ends. And certainly, I think, Antoine asked you a question about the ping pong ball, but I'd like to ask you the question, and it's not really a question. It's about the collaboration between architects and engineers, and you touched on this, where instead of going away and coming back a week later with the column size, you give the column size or the beam size there, but certainly in my experience, it's always been about engineers thinking like architects and architects thinking like engineers, because I think if you don't do that, then you get this wall where the architect says, this is what I want, you go away, make it work, or the engineer saying, this is the way it works, and you can't do what you want to do, architect. And it's that collaboration of the two minds, understanding what each one of them is trying to accomplish, and each of them trying to do what the other one's discipline is trying to do, and really coming together. And I think that it's only when the two of them actually really understand what each is trying to do that you do get design excellence. And it's about the building. And in the end, it's not about engineering or architecture at all. It's about, this design excellence that we're both trying to do.
Yeah, and often it's maybe not answering the question that is asked, but answering a different question, and it might be the beam and column thing is a good analogy. It's not about the size of the beam; it's about should there even be a beam? Should we have a beam? What is it's much kind of deeper. It's sort of stepping much further back and then looking from high level. What are we trying to achieve, and what's the best way to do it? And
yeah,
we do it together.
Yeah, that's a great way of putting it. On behalf of NORR, I want to thank you for that excellent presentation, and we definitely will have you back for either the mass timber project or other projects in your life. I mean, you're working on some very fantastic projects, and we wish you all of the very best. And again, thank you for this one, and hope to see you in Toronto, or we'll see you in London at some point in time.
Thank you very much for the opportunity. And yes, I do hope to come and talk again at a later date.
Okay. Thank you. All the best.
Thank you.
And bye to everyone on the line.